Let me recall. Okay, our final talk for this week is Ernani's talk on Ricci solitons. So thanks him for nice lectures, and here you can go.
Okay, thank you, Mustafa. Let me continue where we stopped in the last lecture. Just to recall that you mentioned this result obtained by Sal and Zhou in 2010. Talking about this result, what they proved that if you have a n-dimensional gradient shrink Ricci soliton complete, then the potential function is has a special behavior. It must be controlled by the distance function square up to a constant, and also is bounded from below by something similar, also a quadratic term. So we talk about this, the behavior of the potential function. So this is the point that you stop in the last lecture. Then what we know now is, you know that if you have a complete, not necessarily compact range solid, we know the scalar curvature is non-negative, and it will be zero only is the Gaussian soliton. Now you know the behavior of the potential function f. And another important information when you are studying non-compact manifolds, complete non-compact manifold, is the behavior of the volume growth. Because we know the volume goes to infinity, but we can say how it goes to infinity. Just to call attention to this, let me put this question about the volume. What can say about the volume growth? So just to compare with the common literature, we call that a result obtained by Calabi-Al, which says that if you have a complete manifold with non-negative Ricci curvature, then they prove that if you're looking for a geodesical ball, and here is P is a fixed set point and R is the radius of this ball, when you're looking for the volume of the geodesical ball, we know that this volume must be bounded by, let me just put it here, it's bounded by CR. In other words, this result says how is the behavior of the volume growth when R will increase. If you define this to be a function depending on R, the result says this function is bigger than equals to CR, then we know the behavior, how the volume growth in this manifold. So what we know is this behavior is optimal because this is exactly the behavior of the volume growth of the Euclidean space. In the case of the Ricci curvature is zero. So that is also another important result related to this when it was proved the upper bound. This is the Bishop volume comparison theorem, the Bishop comparison theorem, which is similar, but now we have a complete manifold, also Ricci curvature is non-negative, and he proved that the volume growth is bounded from both by CRN. Is what you say that is a at most polynomial growth. Okay, then these informations give us how is the behavior of the volume growth around this complete manifold. There are many important results that you can obtain by using this kind of volume comparison theorem. We can obtain a estimate for the eigenvalues. We can obtain rigid results and guarantee some that some tensor has a little norm bounds, and it's very interesting. It gives very important information about this manifold just using volume comparison theorem. So if that result is known, they are a classical result in geometry, is known by assuming that the Ricci curvature is non-negative. It's very natural to ask him about the possibility to prove similar results. Consider now the condition of gradient Ricci solid, because we have a term, a little bit more, a term here, Hessian F, and as well, volume comparison will be useful to prove some rigid results. And in this direction, Haidong-Sao and the Tangzhou, they were able to prove that in 2010 that the same behavior of the Bishop theorem is true for gradient shrink Ricci solid. In other words, they prove that if you have a n-dimensional complete gradient shrink Ricci soliton, then the volume growth of the geodesical ball is bounded from above by polynomial behavior, it's at most polynomial volume growth. Okay, and in fact, this height here, this height is sharp because exactly the growth is estimate that you can check in the Gaussian soliton. However, in his proof, we can see that this constant C depends on the geometry of the unite ball at a point P. It depends on the metric in this point. This constant is not general. And moreover, this is true for R sufficiently large. Okay, so, but we know that this height is sharp, but it's interesting to see if the equality holds if you can back to the Gaussian soliton. So, and very recently, we try to understand this question about the possibility to improve this constant C. But before to do that, let's just mention here the Gaussian soliton Rn delta J, and with potential function F given by F squared divided by 4, this guarantee that the Euclidean growth rate is optimal. So, but how can I improve this constant C to only depends on something general? So very recently, the Tangzhou and Sheng, so myself, Sheng, 2020, 21 archived, 21 in the 22 in the journal, we proved that this behavior is given by this constant times omega n r with this power, or omega n is the volume of the unite Euclidean ball. Now this constant is general, and moreover, we recover the case of equality, because if the equality holds, if and only if this manifold is the Gaussian soliton. Then we now know that how is the exactly behaving. Okay, so now this does not depend of the geometry of the unite ball, because this is the volume of the Euclidean. Okay, so but how about the lower estimate, something like Calabi-Yau theorem, because we proved this upper bound estimate, but how about the lower bound estimate? The lower bound estimate was obtained by Munteanu and GTSS, and the lower bound estimate was obtained by Munteanu, Ovidio Munteanu, and GTSS. So it's exactly the same result of Calabi-Yau for gradient shrink Ricci solitons. Then what you know now is that we know the scalar curvature must be non-negative. We know the behavior of the potential function. We know the behavior of the volume growth. Okay, so now let me also mention two important theorems. We can mention here Hamilton, this theorem. And this theorem says that if we have a two-dimensional MDF, two-dimensional gradient shrink Ricci soliton, then it must be the finite quotient of the Gaussian soliton or a sphere. So, in other words, two-dimensional gradient Ricci soliton and complete, not necessarily compact case is complete class phi. We don't have another thing to do here. Okay, they are complete class phi. You mentioned so. And moreover, just put here a remark, look at that. The curvature here is 0 and the curvature here is positive. We can say that in this case, and in general, in two-dimension, for this specific dimension 2, in general, every Ricci soliton has non-negative curvature. Okay, then in general, two-dimensional Ricci soliton has no negative curvature. Okay, it's clear. Then they are complete class phi. How about dimension 3? In dimension 3, the result is a little bit more. The credit of the result is too large, but the last result that we remove another additional condition that was considered before, but the last result was obtained by Cao Shen Zhu in 2008, but the result was first obtained by Hamilton, Ivey, Newolak, and Perriman with additional condition. And finally, Cao Shen Zhu removed these curvature conditions in order to obtain the result in dimension 3. If you have a three-dimensional gradient shrink Ricci soliton, then it must be the Gaussian soliton or a sphere or S2 cross R. Then again, in dimension 3, complete, not necessarily compact gradient Ricci soliton are also completely classified. Okay. As I said, the result was first obtained by contributions by Hamilton, I.V. Berman, Nee, Wallach, and but we have additional additional conditions. So we turn back for dimension 4 because dimension 2 and dimension 3 gradient Ricci solitons complete, not necessarily compact, are entirely classified. But what you can say about dimension 4? What about dimension 4? So again, let me mention here, similar to the two-dimensional case, when you're looking for this example, we know that this is non-negative scalar curvature, non-negative curvature is zero curvature, so I'm sorry. This is positive and this is positive as well. This is non-negative, sorry. What can say is this third example that entirely classified three-dimensional gradient soliton, they have non-negative curvature, okay? So here in the classification is include the quotient, the finite quotient of these guys, okay? But essentially, it's okay. They are entirely classified. So, but what can say about dimension 4? And now we are interested in not necessarily compact. We are looking for non-compact case as well. So, in dimension 4, we know that the Bud 2 forms can be invariant decomposed as the exam. This we already mentioned that, and we also know that the Riemann curvature operator, the Riemann curvature tensor, can be decomposed as a sum like this, or this first guy is the trace-free part of the value tensor or of the curvature tensor. This is the value tensor, and we have here a combination of the Ricci curvature and the metric. Minus IM JJK minus AJK JIL minus scalar curvature divided by 6 and JJL JIK minus JIL JJK. Okay, so and this guy was our target when you are discussing the compact case, and it's also our target when you're talking about non-compact case. So one of the assumptions that is very natural when you are talking about four-dimensional Ricci soliton is to consider that this guy is zero. This is equivalent to say such manifold is locally conformally flat. Formally flat. Okay. But also we can consider in dimension 4 the assumption of half conformally flat when there's just one piece of this is zero. And this is the assumption of half conformally flat. Okay, this is specific dimension 4. This is for dimension n bigger than equals to 4. Okay, so if this guy is our target, it's natural in order to try to obtain a classification result similar to the three-dimensional one and the second dimensional one, is try to classify four-dimensional gradient soliton. Then you go in the behavioral in the way of to try to obtain conditions over the value tensor in order to obtain some classification result. In the last year, several result was obtained in these directions. A very important theorems was obtained. One of the I'd like to start is a theorem which is obtained by combining result by different authors, some like Eminent, Lanave, Mantegazza, Neil Wallach, Sau, Wang, Zhang, Peter Patterson, William Wiley, and Munteanu and Sesson. And then by using this, the result obtained by them, we can guarantee that in dimension 4, if you have a four-dimensional gradient shrink Ricci soliton, and if you assume that it is locally conformally flat or the value tensor vanishing, we can guarantee that the set manifold must be S4 or Gaussian soliton or S3 plus R. So then four-dimensional Ricci solitons are entirely classified in dimension 4 if we assume this condition of locally conformally flat. Okay, so the same result is true for higher dimension. We are focused here in dimension 4, but the same result, this specific result, is also true for higher dimension. Okay, I remarked here, it's also true for any bigger than equals to 5. Okay, this is a very common result when I'm looking for the value tensor. So it's natural to now consider some weaker condition. One weaker condition dimension 4 is looking for half conformally flat condition. And then this was proved by Shen and Wang around 2011. This was posted in archive. And the result is if you have a four-dimensional gradient shrink Ricci soliton of dimension 4 and assume it is half conformally flat, just appears as 0. Of course, it's the same result if you assume double minus 0, but if you put double plus, not problem, because you can go this direction, just standard orientation. So if double plus is equal to 0, they prove that set manifold must be the quotient, the finite quotient of S4, CP2, S3 cross R, or F4. Okay. So again, we obtain the classification of gradient shrink Ricci soliton. We have a weaker condition dimension 4. This result improved the previous ones obtained by different authors, but in dimension 4, this is a result just for dimension 4 because it's necessary to look for the decomposition of the value tensor in self and self-dual part. Okay, and after that, it was posted in archive, a very interesting theorem obtained by Haidong Cao and his former student, Qin Shen, where they consider the case of bar-flat Ricci soliton. Before to state the result obtained by them, let me recall that the bar tensor is a very common tensor in physics, but now is also common in geometry as well. But the bar tensor was introduced to study conformal relativity, but now is very common also in geometry as well. But the bar tensor is given by a combination of the second derivative of the value tensor and a multiplication of the product of the Ricci tensor by the value tensor. So here's the definition for arbitrary dimension n bigger than equals to 4. This holds for dimension, this definition is for dimension n bigger than equals to 4. Okay? While the dimension is equal to 3, the definition is a little bit different. It's given by the bar tensor is the derivative of the cotton tensor, the divergence of the cotton tensor. This is the cotton tensor. So the bar is a little bit different of another tensor that we introduced, but it is very interesting when you compare with the another ones. Let me just put in here the notes that this is the cotton tensor. And now let me give some interesting facts between the bar tensor and the another one that you already discussed in this lecture. So we say that a remaining manifold, it is bar flat, of course, if this bar tensor vanish, and the bar tensor is identically 0. Okay, when this tensor here that you define above, it is 0. In this case, we say this manifold is bar flat. Why this is will be important for us? The first is because if the value tensor is 0, it's very easy to check that the bar tensor necessarily is 0. The converse statement is not necessarily true. Okay, it's not true. So it's easy because if the value tensor vanishes, these two terms disappear. Then, of course, the bar tensor is 0. But the converse statement is not true. So another fact is if double plus is equals to 0, in other words, if my given manifold of dimension 4 is half conformally flat, then the bar tensor is 0 as well. Okay, in Hoagly speaking, when you assume the bar flat condition, such a conditions will improve half conformally flat and locally conformally flat conditions that you already considered. It's clear? Any question about this guy? No? Okay. So another information is if my manifold is Einstein, remember Einstein, when the Ricci curvature is proportional to the metric, I also have bar flat. And then the bar flat condition also improves the Einstein condition. It's a weaker. 5, bar flat metrics in dimension 4. Now, there's also specific in dimension 4. Dimension 4. Bar flat metrics are critical metrics of the following functional, conformally invariant functional given by this expression, the integral over m of the norm of the value tensor square. This is this guy here inside is the value tensor with respect to this metric. Okay, then the critical points of this functional are precisely bar flat metrics. Then they appear as critical points of a remaining function. So this is just for giving a very clear idea how this is interesting, this assumption. And with this condition, we have this theorem by Sao Chen, published in 2013 in the Duke Journal, where they prove that to have a four-dimensional gradient shrink Ricci soliton with bar flat, then such manifold must be necessarily or Einstein or the Gaussian soliton or S3. So this assumption improved the previous one's results. Okay. So again, like the theorem in dimension for half conformally flat condition, I have here a remark is that this result is in fact true for any bigger than equals to 3, high dimension, or any dimensions. Just put outside the dimension 2. It's very interesting. Of course, you need to change here as the dimension here is taken account. Okay, if you have it as n, will be here as n-1 times the Euclidean factor. So there's very important classification result that in certain sense stop the result in the direction of to look for half conformally flat, locally conformally flat, or bar flat condition. On the other hand, there is another way to analyze the situation of the W that it was considered by Fernandes Lopes and Garcia Hill and Ovidio Monteano and Natasha said. They consider the problem of to classify Ricci soliton under a vanish condition, the Weyl tensor, but now assume that this Weyl tensor is harmonic. In other words, they show that if you have a four-dimensional gradient shrink Ricci soliton that is M4 GF, then, oops, sorry, let me put here the condition. With harmonic Weyl tensor, which means that have the divergence of the Weyl tensor vanishes, then it must be Einstein S2 cross let me put it first. The Gaussian soliton S2 S3 cross R or S2 cross R2. So this was the result proved by them. And now assume the condition of this guy is harmonic Weyl tensor. This is weaker than consider the assumption of locally conformally flat, but there is no connections between the bar flat conditions. One does not improve the another one. They are, you can say they are disconnected. However, both conditions improve the locally conformally flat condition. This result is very nice. And that is something interesting that I like to call attention here, which is this example S2 cross R2 that you did not skirch yet. Okay, S2 cross R2. Observe that in all classification have S3 cross R, the Gaussian soliton, the Einstein case. In all result, I can get this. And here I have CP2 and also S4, but we don't have here S2 cross R2. And then this example is, let's call attention right now. I will talk a little bit more about this example in a few minutes, but this will be one object of interest for us. And this result obtained by combining results of Fernando Lopes, Garcia Hill, Munteanu, and Natasa Ceso was recently improved by different authors. That means, for example, a paper by Peng Vu, Vu and William Wiley in 2018, very nice paper, where they assumed the condition of harmonic self-dual part tensor just appears. And then, of course, this is for dimension 4. This result proved by Munteanu and Natasa Ceso and Fernando Lopes and Garcia Hill also holds for dimension higher. This is true for any bigger than equals to 3. Okay, so but in the specific dimension 4, we have this improvement obtained by Vu and Wiley. Just assume that the self-dual part of the biotensor vanishes. So there is also another improvement of the result obtained by Catino and 2 collaborators in 2017, Giovanni Catino from Italy, and what they consider the Fourier divergence of the biotensor. We know the biotensor is a guy, a 4 tensor, then I can take at most 4 derivatives. Then he consider this order in the derivative and prove the same classification result. Okay, of course, here, just in the paper of Vu and Wiley, he appeared 1 guy more, which was CP2. Okay, but the idea is the same. So, as I said, this example of Ricci soliton S2 cross the Euclidean space is one. It's one object of interest for us in the last years. This example has a nickname. Some guys call him of the bubble shit, which is it's very nice because it's a very nice nickname because we have here a sphere product with a plane. We have to take the traditional metric, the product metric, and the potential function is only necessary to take fx, y, or x is a vector in a sphere, y is a vector in the plane, and this is the norm of x squared divided by 4 plus 1. This combination, this normalization, is just to guarantee that we have this equation with 1/2 here. Okay, because I'm very interested in this normalization just to take result more clean. With this, we know that, for example, if you're looking for the decomposition of the Ricci curvature, if we're looking for the matrix and diagonalize this matrix because it's symmetric, we know this A value must be 1/2, 1/2, 0, 0, and another guys must be 0. In particular, if you take the trace, I can guarantee that the scalar curvature of this guy is equals to 1. Okay, this will be important for us. So another interesting fact here about this example, there is a Keller Ricci soliton, and the double plus, which is a term that appear many times when you are looking for dimension Ricci solitons. We know that in the diagonalization of the matrix associated to this guy, we know this A value must be 1/6, 1/12, and 1/12 as well, but with minus E and 0 in another terms. So this is an example very that attract a lot of attention in the last years. And let me give some comments about him and why this example also call attention. In order to do that, let me just call attention for one fact. We talk about some examples like the Gaussian soliton. Let me change here the color just to call attention a little bit more specific. We have, for example, that we'll discuss a little bit more. The Gaussian soliton, a sphere, CP2, S3 cross R, and now S2 cross R2. What these examples have in common? What these examples have in common? They have constant scalar curvature. The first, the second, the third one are Einstein. The another one are not Einstein, but they have constant scalar curvature. And this fact call attention to the classification of. I'm sorry. I'm in my office. This is common here. So they have constant scalar curvature, and what I can say, it's natural to ask about the classification under this constant scalar curvature condition. This is one question very common in the literature about Ricci solitons of four-part conjecture. So, and in the direction to give an answer to this question, very recently, not too recently, I believe 2015, I'm not sure, but a result obtained by Garcia Hill and Fernandez Lopes. Let's put it like this. They prove the following: if you have a four-dimensional gradient shrink Ricci soliton, complete, not necessarily compact, and if you assume that the scalar curvature it is constant, they prove that the scalar curvature must be 0, 1, 3/2, or 2. Why appear these values? These values are taking account our normalization. Okay, here we are consider the equation of shrink Ricci soliton to be here 1/2. Lambda is to be 1/2. If you replace here 1/2 in the lambda by lambda, for example, the value here will be lambda, and it will be twice lambda, and just take the value here. Let's put lambda 1 will be 2 lambda, and lambda will be 1/2. We can just take the combination over there. So, but with this normalization, the value must be, the possibility will be just this 4 possibility. And they go more in trying to obtain the classification of four-dimensional Ricci solitons with constant scalar curvature. And they prove another very nice fact is if they prove that if the scalar curvature is equal to 0 or the scalar curvature is equal to 2, that it means the first case or the last one, then such manifold must be, such Ricci soliton must be Einstein. In other words, if the scalar capital is 0 or 2, we obtain an Einstein Ricci soliton, then we classify such a Ricci soliton. Okay? Then we have more possibility because we have more two possibility here. The next possibility analyzed by them is the case of this scalar curvature equals to 3/2. In this case, they were able to prove that such manifold must be S3 cross R. Then this is also classified as well. Then the only remaining case was the case of constant scalar curvature equals to 1. And this questions was open for a long years, I believe 8 years. And very recently, the Tangzhou and Shousheng, 2021, they proved that if we have a 4-dimensional gradient shrink Ricci soliton with constant scalar curvature equals to 1, and again, we are consider all normalization when lambda is equals to 1/2, and they were able to prove that such manifold must be S2 plus R2. Exactly the example that you discussing here. Exactly this example which has constant scalar curvature equals to 1. And then they complete the classification because they solve this last one case. In other words, by combining the result obtained recently by the Tangzhou and Shousheng with Garcia Hill and Fernando Lopes, we can say that now we have this theorem. If we have a 4-dimensional complete, not necessarily compact, 4-dimensional gradient shrink Ricci soliton with constant scalar curvature, then it must be the Gaussian soliton, a sphere. I can put like this. Is or Einstein, or the Gaussian soliton, or the S3 cross R, or S2 cross R. It's completely classified in dimension 4. However, the problem, sorry, X column is not good. However, the problem is still open for dimensions, any bigger than equals to 5. And this is the one problem that I like to leave here. This is our open problem, which is essentially try to prove the similar result for higher dimension. Okay, this is still is a open problem, still unsolved for higher dimension. Several times the fact about the dimension 4 is very important. Okay, some arguments in dimension 4 are very crucial. In other times, dimension 4 becomes the problem more difficult. Depends on the situation, but the dimension is really important here. So, in order to present another open problem, when you're talking about non-compact, complete, not necessarily compact Ricci soliton, let me turn back to this to the classification that you mentioned at the beginning of the talk. We said that in dimension 2 and 3, we mentioned this result, dimension 2 and 3, Ricci solitons are complete classified. One fact that we have from this result is that every two-dimensional and three-dimensional gradient shrink Ricci soliton, complete, not necessarily compact, has non-negative curvature. Then it's very natural to ask if the same holds when you go to higher dimension. If it's true, if dimension 4, every four-dimensional complete gradient shrink soliton has non-negative curvature. So let me say a few facts important. The first one, we know that in dimension 2, two-dimensional and three-dimensional gradient shrink Ricci solitons are classified. The same holds and two-dimensional and three-dimensional gradient shrink solitons are complete classified. Also observe that in dimension 3, we also know that the positivity of the Ricci curvature is not preserved. I'm sorry, in dimension 3, the positive Ricci curvature is, in particular, because the sectional curvature in dimension 3 depends only of the Ricci curvature, then I can put here the sectional curvature. Is preserved by the Ricci flow in dimension 3. But when you go to dimension 4, this is not long true. Okay, we know that by our result, from our result proved by Davi Massimo, and that is also a very interesting paper more recently by Renato Beccioli, a collaborator, which shows some, which implies that the Ricci, the positive Ricci curve is not preserved by the Ricci flow in dimension 4. So then in dimension 4, the behavior essentially change. Okay. We also know that two-dimensional and three-dimensional gradient shrink soliton has let me put like this, much more specifically. The curvature of two-dimensional and three-dimensional gradient shrink Ricci solitons is non-negative. This is a consequence of the result that I mentioned. Okay. What we have here is that, in particular, this implies that the Riemann curvature is controlled by a constant times the scalar curvature. This is a consequence of this classification dimension 2 and dimension 3. Then in dimension 2 and dimension 3, we know that the Riemann curvature is controlled by the scalar curvature. Okay, because the classification of results, look at that. In the classification of two-dimensional and three-dimensional Ricci soliton, we cover examples with constant scalar curvature. Then this upper bound there is a constant factor. Oh, this guy has constant scalar curvature, and in the above case, in two-dimensional and three-dimensional case. We know that there are examples of Ricci solitons without constant scalar curvature in dimension higher, dimension 4. The example obtained by Haidon-Sao and Nari-Koizu, and CP2 connects some with minus CP2, has a non-constant scalar curvature. But in dimension 2 and dimension 3, this classification result guarantee that it necessarily has a constant scalar curvature. Then when you back to this estimate that I put in here, we can guarantee that this estimate holds in dimension 3. But what can say about this in dimension higher? So in dimension higher, this is not necessarily knowing. Let me first mention that in dimension 4, the Ricci curvature is not the positive of Ricci curvature is not preserved. Okay, and there is a very interesting example obtained by Fuhrman, Ullmann, and Knopf, which guarantee that in dimension 4 and higher, the Ricci curvature can be mixed, can be chain of sign. In particular, the sectional curvature can be chain of sign. So it is not expected to show that the Riemann curvature is non-negative. But there is a theorem. There's a theorem obtained by Neighbor in 2010, just to be more specifically, which says that you have a four-dimensional and complete gradient shrink Ricci soliton, and assume that it's non-flat. In other words, it's not the Gaussian soliton. And if the Riemann operator is bounded, and non-negative, then the unique possibility is to be S3 cross R or S2 cross R2. Of course, if you remove this, you can put here the Gaussian soliton. So, however, this example that I mentioned, obtained by Fuhrman, Ullmann, and Knopf, guarantee that this guy can be can be negative in this example. So this classification result is not the full classification expected. Okay, so but very recently, I know that this value can be negative. However, it is expected to prove that something like the Riemann control by a constant. Because if you look in the norm, I mean, including the negative case, there can be appear. And in very recently, in this direction to analyze this situation here, Ovidio Munteanu obtained a very beautiful theorem which opened doors for another interesting questions. And this theorem was proved by Ovidio Munteanu and Japin Wang in 2014, where he proved that if you have a four-dimensional gradient shrink Ricci soliton with bounded, and he bounded by a constant, scalar curvature curvature. For example, R less bounding for on a constant are not, for example. Let me put A here. Scalar curvature controlled by a constant A. A is a constant. And then we have exactly the behavior, expected behavior. This is controlled by a constant on M. Exactly. Another word, this behavior is exactly the expected behavior in general. Some results, similar result was obtained for gradient shrink gradient steady Ricci solitons. Here is gradient shrink. So this is a very important result obtained in 2015 about the classification of four-dimensional gradient shrink soliton, because the curvature behavior will be very important in order to obtain a complete classification result. So this assumption will be is the condition, the additional condition in order to obtain this. It's a question about the possibility to remove these assumptions. Or in other words, there is a question about the possibility to prove that every four-dimensional gradient shrink Ricci soliton has bounded scalar curvature. Okay. So very recently, last year, we looking more carefully this theorem obtained by Munteanu and Wang. One remark that I'd like to mention here at this moment is, if you recall the definition of Ricci solitons with normalized lambda, we know that the scalar curvature and nabla f squared equals to f when you take a normalization of the potential function f. And this equation is known as Hamilton's equations. This equation says that the scalar curvature in general is controlled by the potential function f. Okay? And we also know that this control should be a quadratic one, because we know from the estimate proved by Haidong-Sao de Tangzhou, this behavior here is a quadratic behavior. So very recently, taking account this behavior, because this holds in general, we assume a weaker condition than the condition considered by Munteanu and Wang in order to obtain the result, this result, and so 2021. It's a paper in Crowley, where you prove that if you have a four-dimensional gradient shrink Ricci soliton, the same complete gradient shrink Ricci soliton, and our condition is the following: suppose that the scalar curvature is controlled by f as a constant a, where epsilon is a number less than equals to 1. In general, you know the scalar curvature is less than the potential function with the constant 1. What I'm asking here is just consider this value is strictly decimal, strictly less than 1. Just this condition. Okay. And a is a constant. So let me just. Under these conditions, we are able to show that then we are able to guarantee that the norm of the Ricci curvature is bounded. Okay. And also the norm of the Riemann curvature is also bounded. It's controlled by the potential function. So in particular, if you take epsilon to be 0 here, you obtain the condition considered by Monte and Wang, and the epsilon equals to 0, you recover the result. And here we want to assume that this scalar curvature admits a quadratic control by the potential function f with epsilon less than or equals to 1. So, however, it remains open questions about the possibility to remove this condition. Okay, obtain the behavior of the curvature and on 4-dimensional gradient-rich solitons without this condition on a scalar curvature, or maybe take something weaker. So the result stands the curvature estimate obtained by Monte and Wang, and the open problem that I'd like to finish the lecture is about the possibility to remove this condition. So that's all. Thank you.
All right, thank you very much. Any question from the audience? All right, thanks for nice presentation and nice results. So it made us the topic much more intuitive and interesting for us.